All right. Hi, everyone. Thank you very much for watching this recorded presentation. My apologies for not being able to attend the LRGF SSGF annual review this year, but I'm excited to tell you all about my dissertation work, focusing on spectral line shape calculations in dense stellar plasmas with my advisors Thomas Gomez and Don Winget, which I did at the University of Texas at Austin with substantial support from the SSGF program here, as well as Los Alamos National Laboratory. Before I get started, I do want to give a very special thank you to some of the many wonderful people that I've had the opportunity to collaborate with over the past few years, including many people at University of Texas at Austin, Los Alamos National Laboratory, and Lawrence Livermore National Lab as well, where I did my SSGF practicum. Now, to just go ahead and dive right in, my thesis work is all about something called the radiative opacity, which describes how light gets absorbed or scattered by some material. So if we consider light hitting some plasma, some questions we might want to ask are, well, how much of that light gets transmitted through? How much of that light gets scattered off into some other direction? And how much of that light gets absorbed, never to be seen again? What we're asking when we ask these questions is, what is the opacity of the plasma? How opaque is the plasma? And coming from an astronomy department, we care often quite a lot about opacities because opacities shape the internal structure of stars, like our very own sun, where the dominant energy transport mechanism is very often radiation transport, photon transport, which is sensitive to this radiative averaged opacity we call the Roslin mean opacity. But we also care about opacities as it relates to stars because opacities shape the stellar spectra that we see, the light that we see emitted from neighboring stars. So if we consider something like a white dwarf star, for example, which is what most of the stars in our galaxy will eventually become, and we look at this thin outer photosphere, what we see is that the spectrum of light that it emits is highly shaped by the opacity in that stellar atmosphere. So if we want to model stars well, we better be able to model opacity as well. Now, what I'd like to do for this talk is start off with a very brief crash course on something called bound-bound opacity specifically, and then I'll talk a little bit about my specialty, which is line shape theory. And then I'd like to talk a little bit about a couple of my favorite projects from grad school. So I'll start off by talking about something called pseudoatom microfields in solar plasmas. And then I'll finish by talking about something called quasi H2 plus, which shows up in these hydrogen atmosphere white dwarf stars that we see all around us. Now, first up, let's talk about bound-bound opacity. Bound-bound opacity specifically refers to this photon absorption process where we excite an electron between two different bound atomic states. So a photon comes in and it, say, excites an electron from this n equals 1 ground state orbital to something like this n equals 3 excited orbital that's still bound. And this bound-bound opacity is distinct from something like bound-free or free-free opacity because the final state is not one of these continuous positive energy free states. Now, there are a whole bunch of different naming conventions for these different bound-bound transitions that we can observe. Some of the most common here I've labeled are called the hydrogen-Balmer series. So these are transitions where the initial state is n equals 2 in a hydrogen atom. And so if we want to calculate something like a hydrogen beta line shape profile, all that is the bound-bound opacity distribution for this n equals 2 to n equals 4 H beta transition. So on the left here, this is a typical line shape calculated with two different levels of approximation. The y-axis here is simply the opacity or the absorption from this H beta transition, and the x-axis is the wavelength or the frequency of light getting absorbed or emitted. Now, to orient ourselves, I thought it'd be helpful to show briefly this visual opacity dictionary, where this is the opacity that you might see at something typical of, say, a hydrogen stellar atmosphere. Again, the x-axis here is simply wavelength. The y-axis here is the opacity or the absorption. And what you see is that in part of this frequency range, the opacity is dominated by these bound-bound transitions, which we've labeled H beta, H gamma, and so on. But then part of the region is dominated by bound-free transitions, which gives you a nice smooth, continuous source of opacity. So what we're focusing on is specifically these bound-bound transitions, where if we just want to label the H beta line shape profile, that's what this red curve is. So near the central line core of a given line shape profile, that's really the dominant source of opacity. And then as you go out to the far line wings for a given transition, these line shapes start to overlap with each other and contribute more of a smooth, continuous source of opacity. Now, calculating the shape of one of these line shape profiles, calculating the width, the broadening, the line center is really what we're after when we try to calculate line shape theory. There are a number of different physical broadening mechanisms that can contribute to this final line shape profile. One of these is natural broadening, which is related to Heisenberg's uncertainty principle, but that's usually pretty small. Another common one is something called Doppler broadening. This is the classic Doppler effect, with atoms moving towards you or away from you, such that they absorb redshifted or blue shifted light. We also often care about magnetic splitting or Zeeman splitting, which can move these transition energies around in frequency space or wavelength space quite dramatically. But the main thing that we're going to focus on here is something called pressure broadening, which is broadening from charged or neutral neighboring plasma particles. Specifically, we're going to focus on something called Stark broadening, which is broadening from ultimately electric fields. So if you imagine, say, an atom in a dense plasma with all these free electrons and charged ions flying around, those plasma particles are going to generate electric fields, and those perturbing electric fields shift the transition energies at which these line shapes show up, and that Stark broadening is what often is the dominant source of broadening in many dense plasma applications like our own sun or like neighboring stars. So our goal here is really to try and calculate Stark broadening as accurately as possible. Now, first up, I'd like to talk a little bit about this project I worked on modeling pseudoatom microfields in dense solar plasmas. The motivation here is that we can look at our sun, we can take very high quality observations of the sun, and we can try to compare solar observations to solar models. And we would expect those to agree very well. However, what we find in practice is that solar observations tend to suggest that the opacity in the sun is quite a bit higher than what our models predict it should be. So if we look at this plot here on the right, this is a plot of the relative Roslin mean opacity differences, this relative average opacity in the sun throughout the solar radius. So here at 0, 0, this is the central core of the sun where fusion happens. And over at 0.7, this is the outer region of the sun. This is closer to the surface of the sun, where the opacity tends to get a little bit weaker, and eventually convection takes over as the dominant energy transport mechanism. Now, the three different models here in the bottom, these are different opacity models. One from Livermore, one from the French CEA, and one from an Israeli university. And for the most part, these opacity models are all in pretty good agreement with each other as to what the opacity should look like inside the sun. However, the problem is that these opacity models really don't match up very well with solar observations. This shaded blue region is the opacity that you need in order to match solar observations. And so what this is showing us is that the opacity in the sun tends to be underpredicted if we compare it to observations by about 10 to 30%, depending on what region of the sun we look at. So this is frankly rather concerning. We would certainly like to be able to model the sun. We'd like to be able to validate that our opacity models work well. But these solar observations are saying that there likely are some problems with our opacity models. So what this project focused on was on trying to improve the way we calculate something called a plasma microfield. A microfield is a probability distribution of electric fields generated by ions. So if we look at this plot here on the left, these are two sample plasma microfields, one at a relatively low density in blue, one at a relatively high density in black. And as you go to a higher density, what that does is it generates stronger electric fields. So you shift this probability distribution to stronger microfields. And what happens is that those stronger perturbing microfields generate broader line shape profiles. It spreads the opacity out over more wavelengths, over a broader range of transition frequencies. And it makes it look less delta function-like. So if you don't calculate your microfields very well, you're not going to do a good job of calculating your opacity very well, or this average type of opacity we call a Roslin mean opacity. Now, what we did in this project was try to use something called a pseudoatom to calculate microfields for the first time. A pseudoatom is an averaged model of an atom embedded in some plasma, which we solve for using this self-consistent field approach on the right, very similar to density functional theory. So we guess at what the effective electric potential is around some nucleus in a plasma, and then we use that initial guess to solve for the electron wave functions. We use those wave functions to solve for the electron density, and then we solve for a new effective electric potential using that guess of the density. So we go through this loop over and over again, and the hope is that eventually we converge to what we call a self-consistent solution, where we get a potential that gives us a set of wave functions, which gives us a density, which gives us back our same electric potential. Now, the reason we go through all of this is that we can use this self-consistent field approach to calculate detailed electronic structure, even for heavy metals that we might find in the sun, even for really high temperatures, like hundreds or thousands of EV, millions of Kelvin, and even for very high densities, up to and beyond solid density, just like what we see in the sun. And crucially, we can also do this for all kinds of electron configurations, not just for, say, averaged Fermi-Dirac electron configurations, like what you typically see in density functional theory calculations. By doing this, we can calculate detailed electronic structure all throughout the sun, from the very central fusing region where it's really hot, really dense, to the outer layers of the sun where it's a lot less dense and a lot less hot. To actually get the microfields, what we do is we run molecular dynamics simulations. And our hope here is that by including this detailed quantum electronic structure from our pseudoatoms, we hope to do a much better job at calculating plasma microfields at these really hot, dense conditions, where we expect traditional methods to start to break down. And sure enough, that seems to be what we find. If you go to the outer layers of the sun, where the solar radius is, say, 0.7 of the total solar radius. What we find is that at these relatively low density conditions, like 1/10 of solid density, we agree very well with established models. So these are three different microfields on the left, our new models in green, two established models are in black and blue, and they all give pretty similar results, which result in pretty similar line shapes. So this is reassuring. This is what we expect. When the density is low and everything is relatively easy, we get good agreement. But as you go to higher densities, say if you go to a solar radius of 0.5 now, what we find is that as you go to these denser conditions, we tend to predict stronger microfields, which generate broader line shape profiles. And this is encouraging because as you broaden out these line shape profiles, you actually increase the Roslin mean opacity. And so this helps move us in the right direction towards helping understand why our current opacity models are underpredicting the expected opacity in the sun. Now, the few minutes I have left, I'd like to talk briefly about something called quasi-H2+, which shows up in hydrogen atmosphere white dwarf stars. Hydrogen stars are really great for line shape theorists because they should help us validate simple line shape theory. A typical hydrogen atmosphere white dwarf star might look something like this cartoon on the left. Carbon, oxygen, neon in the core, maybe a thin layer of helium around that, but the outer region is just hydrogen. So when we look at spectra from these stars, like what you see here on the right, that spectra should be dominated just by hydrogen opacity, which is relatively simple. And so what we would expect is that if we generate, say, plasmas at something like the Sandia Z machine, and we generate a hydrogen plasma at the same temperature, the same density as a white dwarf star photosphere, and we look at spectral lines from these experimental platforms at the same temperatures and at the same densities as white dwarf stars, what we would expect to see is that our theory works really, really well at these conditions. But what we see in practice is that depending on which spectral line you fit, depending on which bound-bound transition you try to model, you actually get very different densities, very different conditions for the same plasma, which is concerning. That's telling us that something about our theory probably isn't working well. And these discrepancies are held up not just by experimental data, but again by astrophysical data as well. So what this project was really focused on was trying to answer this question of, well, why can't we fit even simple hydrogen lines in these hydrogen stellar atmosphere conditions? So what we focused on is the modeling of something called a quasi-molecule. A quasi-molecule is not a bound molecule. This is an unbound, transient close collision that temporarily induces molecular-like structure. So if you have a plasma that's really, really hot, so you can't form bound molecules, but also really, really dense, so that, say, a hydrogen atom and a proton can, with some likelihood, pass by each other at a really close internuclear separation, you can form something like a transient H2 plus system. And we know that these transient H2 plus systems exist because we can observe them in these hydrogen stars. So like, for example, this spectra here on the left, this is an ultraviolet spectra from a hydrogen atmosphere white dwarf star taken with the Hubble Space Telescope, where we see these really big absorption features from quasi H2 plus. And we see these for quasi H2 and for quasi H2 plus in a whole bunch of different lines. Now, what we did here was we built something of a new simulation-based approach for modeling these quasi-molecular collisions. Effectively, we built a charge exchange model to put into simulation line shape codes. So this animation that I'm showing here, this is one of my favorite animations to show. What's happening here is that initially you have a hydrogen atom at the origin at 0, 0, and then there's a proton that's passing by on some random close trajectory, but it's not stopping. It's not forming a bound H2 plus system. The proton's just passing on by. And what's happening on the right-hand side here is the color bar corresponds to the electron wave function of this transient H2 plus system from our simulation line shape code, where we've put in what we call a change of basis procedure to selectively operate in either an atomic basis or a molecular basis when it's more appropriate. And by operating in a molecular basis selectively, what happens is that we capture this charge exchange process quite naturally. So you can see as the proton flies by, the electron that's initially centered on the origin here starts to be shared by the two protons. It starts to oscillate back and forth. This is effectively charge exchange that we're modeling, but it's also accounting for this transient molecular-like structure that forms, which affects how light gets absorbed in these hot, dense plasmas. Now, the way we validate this is by comparing to, again, astrophysical data. This is, again, a spectra taken from the Hubble Space Telescope on the left. The data is in gray. The blue, black, and green curves are previous, older, more approximate models of this quasi-molecular absorption. And then our new work here is shown in red. And frankly, what I think this shows is that our new approach, which does this with a simulation line shape code and models this charge exchange process, I think does a remarkably better job of agreeing with the astrophysical data, of matching reality than anything that's been done before. So we're really, frankly, quite excited about the success of this quasi-molecular approach, and we're hoping to extend this quite a bit to many more systems and many more types of collisions in the near future. Now, to wrap up, I'll just put up this brief summary slide as for what I'm doing moving forward. I have accepted a position at Los Alamos as a director's postdoctoral fellow. So I will be here in Los Alamos for at least a few more years. And with that, I will go ahead and wrap up. Thank you very much for watching again. Another very special thank you to the SSGF program and the Krell Institute for supporting me over these past few years. And with that, I will log off. Thank you very much.